This PowerPoint presentation covers section 14.3 from the Acid-Base Equilibria chapter in our textbook. The topic of this section is relative strengths of acids and bases. In this video, we will discuss differences between strong and weak acids and bases, the use of Ka and Kb to quantify the strength of an acid or base, how to find Kb if you know Ka, determining the pH of a weak acid solution, and predicting relative acid-base strengths based on molecular structure. Before viewing this video, make sure that you have completed the reading guides for section 14.3. Also, have your copy of the Chapter 14 handouts ready so that you can take notes as we work through this section. HCl, hydrochloric acid, is an example of a strong acid. When we write the equation for its dissociation in water, we use a single arrow to indicate that the reaction goes essentially to completion. The equilibrium position lies very far to the right because the value of K for this reaction is extremely large. If you were able to examine a beaker of HCl on the molecular level, you would see only H+ and chloride ions dissolved in water, and virtually no HCl molecules. HF, hydrofluoric acid, on the other hand, is a weak acid. We use a double arrow to show that this reaction reaches an equilibrium position where both reactants and products are present at equilibrium. In the case of all weak acids, the value of the equilibrium constant is less than 1, and the reaction is reactant favored. In a beaker of dissolved hydrofluoric acid, most of the HF molecules would remain as molecules, and only a few of them would dissociate into H+ and fluoride ions. Again, for weak acids, the equilibrium lies to the reactant side of the equation, it's reactant favored, because we have small K values. Sodium hydroxide is an example of a strong base. Again, we use a single arrow in this equation to indicate that the dissociation reaction goes to completion. This is a strongly product-favored reaction with an extremely large K value. All of the sodium hydroxide gets dissociated. Ammonia is an example of a weak base. When ammonia reacts with water, small amounts of ammonium and hydroxide ions are formed. A double arrow is used to show this equilibrium. For weak bases, the value of the equilibrium constant is small, and the reaction is reactant favored. At equilibrium, there is mostly NH3 molecules with a smaller amount of ammonium ions and hydroxide ions in solution. For strong acids and bases, we can use the stoichiometry tools that we learned in Chem 40 and Chem 50 to determine the concentrations of ions in solution. However, we will need to apply all of the equilibrium tools and concepts that we learned in Chapter 13 to be able to determine the concentrations of ions in solutions of weak acids and bases. Just as we saw that there's a special K value for the ion product constant of water, which we called Kw, we use a term called Ka to represent reactions of weak acids reacting with water. Let's start with the generic reaction for a weak acid reacting in water. If we use Ha as our generic weak acid and show it reacting with water to form A- and the hydronium ion. Since equilibrium constants are always product concentrations over reactant concentrations, the expression for this reaction, or the equilibrium constant expression for this reaction, will be the concentration of HA times the concentration of A minus over the concentration of HA. We define this equilibrium constant to be Ka, and it is the equilibrium constant value for the reaction of a weak acid reacting in water. We can write a similar reaction for the reaction of a weak base reacting with water. Recall that we can use the symbol A minus to represent a weak base. Remember that A minus is the conjugate base of the acid HA. So if we show A minus reacting with water, the products will be HA and hydroxide. If we write the equilibrium constant expression for this reaction, again we have the product concentrations, concentration of HA times the concentration of hydroxide, divided by the concentration of the reactant, A minus. Recall also that pure liquids like water don't appear in the equilibrium constant expressions. We define the K for this type of reaction, for the reaction of a weak base reacting with water, we define it as Kb. Notice the similarity or overlap of terms between Ka and Kb. Many of the same concentration terms appear in each. Watch what happens when we multiply these two expressions together. If we multiply the expression for Ka times the expression for Kb, we have Ka, again, as the concentration of H plus times the concentration of A minus, divided by the concentration of HA. We multiply that by Kb, which is the concentration of HA times the concentration of hydroxide, divided by the concentration of A minus. We see that we can cancel the concentration of A minus and also the concentration of HA. So when we simplify this, we have Ka times Kb is equal to the concentration of H plus times the concentration of hydroxide. But we recognize this term as the expression for Kw. So that shows us that Ka times Kb for a conjugate acid-base pair is going to be equal to the value of Kw, which we already know at room temperature is 10 to the minus 14. This expression is valid only for a conjugate acid-base pair. In other words, the Ka for HF times the Kb for its conjugate base, F minus, would be equal to Kw. But the Ka for HF times the Kb for ammonia does not equal Kw. Remember also that all of the Chapter 13 concepts will apply. Equilibrium constants are temperature dependent, and the size of the equilibrium constant will determine the extent of reaction. The larger the value of K is, the more products will be formed. This chart shows some common acids in order of decreasing strength. The acids highlighted in red at the top of the table are strong acids that dissociate completely in water. The value of their Ka is much greater than 1, and so are not treated as equilibrium systems. The weak acids in purple have Ka values less than 1. Notice in this section that there are both neutral acids like HF, as well as ionic species like hydrogen sulfate and the ammonium ion. Although these ions are not named specifically as acids, they have acidic behavior because they are able to donate a proton to water. Since hydrogen sulfate is a stronger acid than ammonium, a 1 molar solution of hydrogen sulfate would be more acidic or have a lower pH than a 1 molar solution of ammonium. The species at the bottom of the table are technically acids because they do have a proton. However, they are so weak as acids that they do not donate their protons to water. On the left side of the table, we have the conjugate bases of the acids on the right. We just learned that Ka times Kb is equal to Kw for a conjugate acid-base pair. Notice that this sets up an inverse relationship between Ka and Kb for a conjugate acid-base pair. The stronger the acid, the weaker its conjugate base. So the column on the right listing the conjugate bases of the acids is organized from the weakest at the top to the strongest at the bottom. The bases in blue at the top of the table are actually so weak as bases that they're not able to steal a proton from water. The weak bases in purple in the middle are able to take a proton from water and do act as weak bases in solution. At the bottom of the table, we have our strong bases, the ones that react 100% with water to form hydroxide ions. So the Kb values of the strong bases are much greater than 1, and again are not really treated as equilibrium systems, but we use stoichiometry for these. It's the weak bases in purple in the middle that have Kb's less than 1 that we will treat as weak bases. This slide shows a similar table, but with the Ka values of the acids shown. Acids with a larger Ka will produce more hydronium ions than acids with a smaller Ka. We also need to define a new term, pKa. pKa is defined as the negative log of the Ka value. So the larger the Ka, the smaller the pKa. pKa values are useful for buffer calculations, as we'll see in a later section of the chapter. Please note that on quizzes and exams, only Kas and pKas will be provided. You can calculate the Kb for any base if you know the Ka of its conjugate acid using the equation that we just derived, Ka times Kb is equal to Kw. Rearranging that expression for Kb gives Kb is equal to Kw over Ka. Let's practice this with an example. What is the Kb for carbonate? First, you need to identify the conjugate acid of carbonate. The conjugate acid of carbonate is the hydrogen carbonate ion. Looking at the table on the previous slide, we see that the Ka of the hydrogen carbonate ion is 4.7 times 10 to the minus 11. Now we use the expression that Kb is equal to Kw over Ka of the conjugate acid. Plugging in our numbers, we have the value of Kw as 10 to the minus 14 divided by the Ka of the hydrogen carbonate ion, which is 4.7 times 10 to the minus 11. Putting that into our calculator, we get a number of 2.1 times 10 to the minus 4. This will be the Kb of our carbonate ion. Now write the chemical reaction and equilibrium constant expression that represents the Kb for the carbonate ion. Kb means we're talking about carbonate acting as a base in water. So the reactants will be carbonate ion plus water. Bases accept protons, so the carbonate ion will pick up a proton from the water to form the hydrogen carbonate ion. After the water donates its proton, it becomes the hydroxide ion. Equilibrium constant expressions are always the product concentrations over the reactant concentrations. So in this case, Kb for this reaction is the concentration of the hydrogen carbonate ion times the concentration of the hydroxide ion, both of those are products, and divided by the concentration of carbonate ion, which was one of our reactants. Remember that pure liquids like water don't appear in the equilibrium constant expressions. Let's apply what we've learned to try to find the concentration of H+ and the pH of a weak acid solution. For solutions of weak acids, the pH is determined by the extent of ionization, the concentration of H+ produced by ionization. This depends on the size of the equilibrium constant, the Ka value. For a generic reaction of Ha plus water to make H+ and A-, we have our Ka expression. We will use the same strategies as we did in Chapter 13 to calculate the equilibrium concentrations of the H3O+ ion given the Ka and initial concentrations of Ha. For example, calculate the pH of a 0.1 molar nitrous acid solution. So let's see if we can answer the question, calculate the pH of a 0.1 molar nitrous acid solution. To calculate pH, we'll need to know the equilibrium concentration of the H+ ion. Where is the H+ coming from? So nitrous acid is a weak acid. When it reacts with water, it forms the H+ ion and some nitrite ions. What is the extent of this reaction? We'll want to set up an ice table. We're starting with 0.1 molar of our nitrous acid and 0 for the H+ and nitrite ions. I'm going to put quotations around the 0 here. Remember that a pure solution of water should have an H+ concentration of about 10 to the minus 7 molar. Although this isn't 0, it's such a small number that we normally can neglect it when we do these weak acid calculations. We should always go back and check that assumption though. Alright, so our change row is going to be minus X for the nitrous acid and plus X for each of the products, giving us an equilibrium concentration of 0.10 minus X, X, and X. We want to set up our Ka expression. So this is the product concentrations H+ times the nitrite ion over the concentration of nitrous acid. And we see in our table from the previous slide that this should have a value of 4.6 times 10 to the minus 4. So what we want to do is solve this equation for X. On the top we'll have X squared, and on the bottom we'll have 0.1 minus X, and that's going to be equal to our Ka value. We could use the quadratic equation to solve this equation for X. However, since we notice that our Ka value is pretty small, it might be a good idea to assume that our X is small. And again, this will simplify the math. I'm going to rearrange this equation to solve for this X as the square root of 4.6 times 10 to the minus 4 times 0.10 minus X, but remember we're going to neglect the X in the sums and differences. So now we can just put the numbers in and we get a value of X of 6.8 times 10 to the minus 3. Let's check our assumption. We said that X should be small relative to 0.1. So we'll put our value of x over 0.1 and express that as a percentage. We get 6.8%. Unfortunately, this is just bigger than our 5% rule, so to get a better value of x, we should iterate this. We'll go back to this equation here, and this time, instead of neglecting x, we'll put in our first guess for x of 6.8 times 10 to the minus 3, solve that to get a new estimate for x. So again, we're going to take this value, plug it in right here, and do that on our calculator. When we do that, we get 6.5 times 10 to the minus 3 as our result. We want to keep doing this until our answer converges. So this time, we'll put 6.5 times 10 to the minus 3 in here for x. And this time we get 6.6 times 10 to the minus 3. Doing it one more time gives back 6.6 times 10 to the minus 3, showing that our answer has converged. So we've been able to solve for the value of x, but the question actually asked us to calculate the pH. Recall that pH is equal to the minus log of the concentration of H+. Since the H+ concentration is equal to our value of x, that means that our pH should be negative log of 6.6 times 10 to the minus 3. Plugging this into our calculator, we get a pH value of 2.18. So the pH of a 0.1 molar nitrous acid solution is 2.18. Let's look at the second example. If a 0.015 molar solution of a weak acid HA has a pH of 2.67, what is the value of the ionization constant? We don't know the identity of our weak acid, but we can write an expression for it reacting with water to form H+ ions and A-. Ka will be the product concentrations over the reactant concentration. We're looking for the value of Ka, so we're going to need to find equilibrium concentrations of all of these species. So again, we'll want to set up an ice table. We're starting with 0.015 molar of our acid, and again we'll assume 0 of H+ and A- to start with. The change row will be minus x for the reactant and plus x for each of the products, giving us 0.015 molar for the HA, minus x, and x for each of the products. In this question, we're given the value of pH at equilibrium. The concentration of H+ is equal to 10 to the minus pH value. Plugging this in, we find out that the concentration of H+ at equilibrium is 2.14 times 10 to the minus 3. And this is our value of x. So in this expression for Ka up here, we're going to put in our x value for both H+ and A-, which is 2.14 times 10 to the minus 3. And we're going to square that because we have two terms. And we're going to divide it by 0.015 minus x, or minus 2.14 times 10 to the minus 3. We have only numbers in this equation, so we can solve for Ka, and we get a value of 3.6 times 10 to the minus 4. We showed some structures of acids and bases at the beginning of the chapter, but now that we know a bit more about acids and bases, let's review and extend our understanding. There are several classes or types of acids that you need to know. The simplest are the binary acids. These acids consist of a hydrogen atom bonded to one other electronegative element, like chlorine or fluorine. Acids have protons bound to electronegative elements. Oxyacids are one or more protons attached to polyatomic ions that contain oxygen atoms. Some examples are sulfuric acid, nitric acid, and phosphoric acid. Note that in each case, the acidic proton, the one that can be donated to water, is bonded to one of the oxygen atoms. Carboxylic acids all contain a carbon double bonded to an oxygen and single bonded to another oxygen, and that oxygen is bound to an H. This is the acidic proton. In different carboxylic acids, the rest of the molecule can be a variety of functional groups. Acetic acid has a methyl group here, CH3. Citric acid actually has 3 different carboxylic acids attached to a carbon framework. Notice that the hydrogens attached to carbons in these structures are not acidic. That means that they are not donated to water in reactions. Amine compounds that have a lone pair of electrons on the nitrogen atom will act as bases because they are able to accept a proton. The lone pair electrons make the bond to the proton. Bases generally have an electronegative atom with a lone pair of electrons. It's these lone pairs that can form a bond to an H+ ion. Another class of bases are anions that have oxygen, sulfur, or halogens. These will have a lone pair of electrons that can accept a proton. We can make predictions about the relative strength of acids based on their molecular structures. A guiding principle is that anything that weakens the HA bond and or makes it more polar will increase the acidity of the acid. Let's start by comparing some binary acids. For a series of binary acids, the acidity will increase down the periodic table because the bond strength will decrease due to the size of A increasing. So here we would be comparing things like HF versus HCl. We know that HCl is a stronger acid than HF. Why is that? It's because chlorine is a larger atom than fluorine, and so the bond strength between H and chlorine is weaker than the bond strength between H and fluorine. That makes hydrochloric acid a stronger acid than hydrofluoric acid. What about comparing a series of acids as you go across the periodic table? The acidity increases from left to right because in this case, although the size of the bonded atom A stays roughly the same, bond polarity will increase. So here if we compare HF with water, water being to the left of fluorine, or oxygen being to the left of fluorine in the periodic table, we see that hydrogen fluoride, or hydrofluoric acid, is a stronger acid than water. Again, this is due to the fact that the HF bond is more polar than the OH bond, and therefore weaker. And again, remember, if you have a weaker bond, it's going to be more acidic. Give me a second to erase some of this to make room. Okay, here we go again. Now let's look at the acidity of oxyacids. The acidity of an oxyacid will depend on two factors. Acidity will increase as the electronegativity of the central atom Y increases, and acidity will also increase as the number of oxygen atoms increase. The more electronegative the central atom is, the more it draws electron density away from the OH bond. As electron density is pulled towards the Y atom, you lose electron density in the OH bond, thus weakening it. This makes the acid more acidic. Increasing the number of oxygens has a similar effect. Since oxygens are electronegative, the more of them that there are, the more electron density is stolen from the OH bond. In terms of carboxylic acids, we see a similar situation. The acidity of a carboxylic acid will increase as the electronegativity of the attached R group increases. Again, the more electronegative the R is, the more that it will pull electron density out of the OH bond, weakening it and causing it to be more acidic. We've just finished section 14.3. You should now be ready to complete the group work problems 5 through 10 in the group packet.